Okay, so probably just information for you. It's an info update that the quiz for chapter 12 and 13 will be online quiz like last time. But since I believe some students uh, give me advice for not giving you the answer key after the quiz, so yeah, I will turn it off and we will have the quiz. I will set up the time. The duration is probably from the weekend. So from the weekends and then maybe around 5 days. So should be around from 5:14 to around maybe 5:17 or 5:18, maybe 5:18. Okay. This will be the quiz duration. Uh, Total questions is, I believe, it's 25 questions. This will range from short questions asking really short topics that is probably takes around 30 seconds, and the longest one for a question is around 15 minutes. The total, if you look on the 25 questions, this will takes around probably, if you take the maximum duration, probably around 2 hours. So around 120 minutes. This is, I think, the safe time that you can have if you want to takes time for your quiz. Okay, so each question they have different time limit. You need to be aware of. There are two types of questions: multiple choice and fill in the blank. Okay, that's for the quiz. Okay, now if you look back on the maximum minimum value, there are one more section in the 14.8 that I have prepared a video that you need to watch. I hope you already watch because I think later on a quiz on chapter 14 or final exam that includes chapter 14 will also include the 14.8, which is the Lagrange multiplier. Probably if I have time this week, I will prepare another video for uh, further questions on 14.7 and 8. So I will have additional video, maybe one more video for chapter 14. Okay, I hope the video can help. You can also watch the previous video on chapter 14. That is mostly about partial derivatives, the chain rule in partial derivatives. Okay, so you can also check that video. Okay, now today I will start with the chapter 15. Which is the multiple integral. So what multiple integrals means that usually in calculus 1 we deal with the integrations from a to b function of x to x, which means that this is an area under the curve, right? Well, now in calculus 2 at least we will deal with at least two integrals. We say this double integral on some area, let's say area D, of a function of at least two variables, and then this is, we say, dA. It can be dx dy, it can be dy dx. Okay, and this will be a volume under surface of z or fx1, function of two variables. Okay, now to begin with, for the introduction, I will show you the introduction. 15.1, it's about double integrals. over a rectangle, over a rectangle. Okay. Or maybe before this, maybe let me give you another context that we are looking at. That is, if we have, let me check. Row. Okay, yeah. Okay, so we have here our approach for the definition of the integral. That is, we can say that the integral from a to b from a function of x dx is actually equal to limit Sn approaching infinity of our Riemann sum. We can say this is a Riemann sum of f at some point for xi. We say that this is our sample point, that we can take xi from any point from this rectangle, and we can add all those rectangles, and we say that as the per definition that is the integral. Okay, now looking at the double integral, so let our function of two variables, let this equal to z, and let me put another picture, okay, to make it more clear. Okay, so the first introduction is we are going to look at how this surface z equal function of xy will be projected into xy plane. Okay, and now we say that this rectangle, if you see the rectangle, this is practically the sides, sorry, wrong, should be 8ab multiplied with cd, and this is, of course, should be in domain of space of R, and then we can say that, let me make it a little bit to the left. Okay, with A, D, and C. Okay, we have this y and x. Okay, because we remember that in function of two variables, our x and y is both are independent variable. The only one that is taking the rate of change is the z, right? That's in our partial derivative. Now in integrations, it works similar, and we also say that the surface S, they are also real numbers in 3 dimensions, and the way that z will be evaluated depends on the function, and the function depends on the point xy. Okay. Okay, next, what we are going to do with this rectangle here for this A, B, and C, D, next thing that we can do is we can cut cut this rectangle into small pieces, into small rectangle. Okay, hope you can imagine that. And then after that, if we take this, let's just take one example, and we are going to project to the surface. And we are getting our parallel pipe, right? It is called the parallel pipe. Parallel pipe. So if we are doing this to all of this small rectangle, and we make another parallel pipe. Okay, so if we map all these small rectangles to our surface, we are going to have the, let's say, if we want to find the volume of this parallel pipe, the volume will be the area of rectangle, of course, multiplied with height. Now, if we take the small rectangle, then we can say that it becomes the delta of AI. Okay, and then multiply with height. Okay, and then similarly, if you look, maybe I will look on the, let me check whether I have, I think I have, yeah, we take all rectangles and make it into our approximation. So all the rectangles map into the surface. Okay, so each we have not only xi, we have j to determine that we have it is depending on x and y. Okay, it depends on how many n we are cutting a rectangle, and let's say we have a lot of n, so a lot of rectangle, then we might have get approach to the volume of the this geometric shape. Okay, and we say that from here, we can say that the we can start from delta and then multiply with function of x I j y I j of each sample point, right? And we can also say that as n getting large, and not only n, but m also, because we have two sides, right, x and y. So we are going to have a limit, and we have two variables that approaching infinity. That is m and n going to have approaching infinity of the sum, okay, of the summations. That is start m, and then this second one is j, our functions, and then delta of the area. Now we say that this is also the Riemann approximation for the volume. Okay. Okay, so we can simply write, okay, the double integral as in definitions in our introduction here. So the double integral of f function over rectangle R. this will be equal to double integral rectangle R for the endpoints, okay, and the function of two variables x, y, dA is equal to limit Sm and approaching infinity of two summations if provided limit is exists. So this is the first definitions for double integral. Okay. I hope at least the introductions can give you more insight and idea on the double integral. If you have any questions or maybe something to discuss, just let me know, and you can write on the chat box. Okay. Okay, I hope you finish this part. Okay. The most important thing is the bottom one, the definitions. That's the essential part. The other part, I believe you can look on the drawings, the visuals, and from there you can imagine that if we take the slicing and make it small rectangle and make it into a parallel pipe, you can imagine first is you can take the x-axis and take the summations, and you can take the y-axis and you have the summations, and that's why you have two summations that we need to multiply each other. Okay. I think we can move to another page to give you more practical approach for how to use this double integral. Okay, maybe some notes that may be important to take. So if a function has both positive and negative, then volume is the difference in volumes between the rectangle and surface below and above. Okay, this is to show that if the surface is below the xy plane, and if there are another one that is above, and you kind of have like in the, I think in the usual integrals that we have, because it's ideally say that the area is of the function is under the curve, means that this is the area. But what if we have another one here? So this will be defined as positive and negative, right? But I think this is already known for calculus 1. And similar with our approach here, if you have a volume, then this will be the difference. Okay, we have the difference. Okay. Then let me write definition for more officials. If functions is positive, then volume of the solid that lies above rectangle R and below the surface z equal function xy is volume will be double integral R f xy dA. So this we can say that the meaning of double integral means that it's the volume of the solid that lies above rectangle R and below the surface. Okay. And actually, in your textbook, there are some explanation on the double Riemann sum and some example, and also the midpoint rule. But I would like to skip all those because I believe it's pretty much similar to what we have done in a single integral. But the difference, we have a double integral. I thought that we can skip that. So I will just focus on in more practical on how we can look on double integral in more practice. So, for example, we could look into let's say we have the iterated integral. How we iterate our computations in the integration. So if you have computers, you have calculators, and if your calculators can calculate double integral, what does the system or what does the processing inside? Okay, what kind of process? So, for example, if we have the okay, we start from let me check. So let me just write double integral. Okay, our function of two variables. Okay, let me start with is having a, b, c, d. So we define this as a constant a, b, c, d, and then we start to get dx, dy. Let's say we have the dx, dy, for example. What is going in the process is what's happening is first is we are looking at this integrations. Okay, we say it is the integration inside. Okay, this is the first step. So we integrate the one that is inside, and after we get the result, after we plug in a and b, then we are going to have the second step. That's how the iterations will be. So the integral is supposed to be like slicing the onion, but we are starting from the inside rather than from the outside. So we start from inside and then goes outside. Okay, that is the default. Okay, the default. Later on, we will have some theorem on how we can solve further. Okay, let me give you an example, okay, on practice how we can solve this double integral. If we have a function inside, let's say we have a function x squared y, we would like to start with dy and then dx, and then we have 1, 2, and then we have 0 and 3. Okay, let's start from let's write the outside first, and we start from the inside. We start from this dy. So if we have dy, similar with partial derivatives, x squared will be treated as a constant, and we are focusing on y. So we'll have x squared, y squared over 2, right? Okay, and then we plug in 1 to 2, and then still we have dx. Okay. Now we are going to plug in 2 into y. Okay, plug in 1 into y also. So we still write 0, 3, the outside integrations, and we are going to evaluate. This becomes x squared over 2, and this will be 4 minus 1, right? Or we can say that this is 3 over 2x squared. Right? And this is equal to this is half and an x cubed, and then plug in 3 to 0 to 3. This is, we got 27 over 2. Okay. Okay. Now what would be happening if what would happen if I change this integrations order? Okay. What is happening now? So let's see, and we can start with 1, 2, 0, 3 x squared y dx dy. Now we could start with the outside, and then the inside we can start with x cubed over 3 y, and then start to input 0 and 3. So 27 over 3 y, and then oh sorry, it's dy. So dy, and then from here we get 27 over 3 y squared over 2 from 1 to 2. So 27 over 3, this is 4 minus 1 is 3, 3 over 2. So we get the same result, 27 over 2. Okay. Now this gives us another theorem that we might need to write, that is called the Fubini Theorem. Okay. Let me just wait for a moment. Okay, let me wait and let you write for some notes. Okay, let me go through the next slide. Fubini's theorem. This theorem says that if we have a rectangle that is composed of AB for the x and CD as usual for y, we will have that if we have a double integration of xy dA, if we would like to start with dy dx, and then this will be c d a b, we could exchange the order. We could substitute this and becomes dx dy. How to prove this in more mathematical ways? it's a little bit difficult and complicated to prove for now, but we can see, I believe, from the volume that we have. Okay, if we remember the recall in calculus 1, we have the volume that is, we have the cross sections, right? The cross sections A. So if you remember, this is f of x, and we want to, if this is x-axis, if we are going to rotate this, we have the solid of revolutions, right? We have a solid of revolutions, and if we take this as our small pieces, we would have a disk like that, right? And this disk is basically composed of dx and the area. And if we take the area as a function of x, we could write as something like this, right? Now, if we exchange this a into our function of xy, then we can write the area as more intuitive like this. Maybe let me write a little bit goes down here. Maybe write more clearly. We can write it in something like this, and now we have combined these two, so the volume will be integration a b ax dx, and then combine the ax inside here. This will be a, b, and ax will be c, the function of xy dy. I hope from this part we can get more clear way why this Fubini theorem they are correct. Okay, although we already proved that if we take some numbers that it is the same result. Okay, for a constant here, if you have a constant, then if we can exchange the order, reverse the order, the x dy or dy dx, the result should still be the same. Okay, and intuitively, if we remember calculus 1, and if we change the terms in calculus 1 into this function of two variables, we see that we can apply this theorem as well. Okay, and we can also imagine that if we have another argument, that if we have similar approach and we have another one that is having dy for our volume, that we will have dx dy, right? Dx dy. Okay. Now before we start to having a little bit exercise, okay, probably I will show you some property that we will at least use most of this property. Some of the property is pretty familiar, and I believe you already sense that intuitively correct. Okay, so some of the properties are for the double integral. So first, if you have double integrations and c is a constant, first is, of course, you can factorize the c. Nothing wrong with this one. Sorry, dA. This is dA. This is dA. Second point, we have integrations f xy dA. If I want to add with this, not add, if the function inside is having another function, more probably we write plus g xy, and both of them integrate with respect to dA. We can separate this, become each double integrals. Okay, if we have this, then we can also separate the endpoints. So if we would like to divide by 2, we can also do that, and this become R1 and R2. Where the R is R1 plus R2. Okay, and the last one is, I think, unique for this chapter, and I believe it will also useful for your further experience in the multiple integrals. So if you have function of g of x and function of y, hy, like that, if we have this inside double integral, what we can do is we can group each variable. We can group each variable. So for example, a, b for dx, and the c, d for y. Let me give you a more depth thought for the last one. Okay, I'll be giving you a few minutes to finish this note, and then we can move to another page. Maybe let me. Okay. Okay, I will move to the next page. If you want to like screenshot, I think the first three property is, I think, familiar. It's similar to what we have in calculus 1, right, in the singular integral. But the last one is it's uniquely in our double integral in this chapter. Okay, let me go through the next section. Okay, so if we have not R, let me write in more. Let f xy is function g of x and then function h of y, and R, let's say typical R, AB multiplied with a CD for the rectangle. Now, if we take the Fubini theorem, we say that this is our integrations. Then we can set up. Let's say we have gx, hy, and then let's say we have dx, dy. So we have a, b, and c, d. Okay, let's say we start with this. So first, we are looking at the inside integral. Okay, let's say we are going to have integrations of the with respect to dx. Okay, now then we are having that we can write the integration as c, d, and then we can set hy as a constant, right? As a constant, because we are just focused on dx. So we can write the hy here, and then integral. Oh, sorry. Let me just write hy first, and then integral, or maybe different color. We choose different color. So integral a, b, g of x, dx, and then dy. And we start to write like this. Make a little bit smaller to give clear that we are going to show you that what's happening here. And because of this, we already have this as our result of integrations. Then the rest is integration with respect to dy. Okay. which is actually just affected this function of y, right? We can write this, or we can write the x first. So a b g of x dx, and then we can write the latter part function of y. Okay, this is a little bit intuitively proving why the functions can be written and can be grouping in this way. Okay, so we can write like this. Okay. Probably any questions if you have, if you want to ask. You can write in the chat box if you have questions. Before we end this section 15.1, one more notes for 15.1 is the average value. As you remember, if you recall the calculus 1, that if you compute the average value, it will be equal to 1 over b minus a, and then the integration f of x dx from a to b, right? It's pretty much saying that it's a point that it's between the value, the maximum and the minimum value for the functions. Okay. Now, in a similar way, in our double integral, we will have average value equal to, now we have a of r, which means the a of r is area of the r, and then this is double integral r and then f xy and dA. And if the function is positive, we could write this AR multiplied with the average equal double integral. So we can say that our double integral is actually consists of two components, the area and the average. So we can say it's as our double integral. As we might also know that this is pretty much describe the volume is area and then height. Okay, area, height, and in the terms of average, it means that the whole sections over the rectangle. We can say that within the average, if you multiply with the area of the rectangle, you will get the same result as the double integral. That is the volume of the area as well. Okay. I hope you get ideas from this average value. Okay, we can have some practice example. Let me check the question. Okay. Okay. We can start with, let me check. We could start with some example. Example. Let's compute some of the double integral. Well, we can start with we start with 0, 1, and 0, 2, y, e, x minus y, dx dy. The first one, the second one is 1, 4, 1, 2, x over 1 plus y over x, dy dx. Okay, we can start with these two. So you can try this for a moment, okay, for a few minutes. Okay, we can have this 2-3 minutes or maybe 5 minutes to try these two questions. And after that we can continue to 15.2. Anyone solve the first one? I think the first one, the answer is a little bit complicated. The solution is a little bit complicated. It relates to E, right? E something, equation of E. And remember, if you remember the calculus 1 integrals technique, like the substitutions, the integration by parts, trigonometric integrals, and a lot of techniques that you already should have learned before. All the techniques may require at some points for solving the integral. Okay, so if you need to review some of the integration techniques, I believe you can go back to your notes, your review notes, or even previous videos of the calculus 1. If you go to the YouTube in my section, I create a playlist. So if you are just want to look on some of the lectures before, you could go to calculus 1. I make a playlist in those videos. I make a playlist, and for calculus 2 also I create a playlist, so you could track all the schedule, okay, all the recordings. Okay, is there any question from here? Do you have any difficulty? Well, let me just show you how to solve it. The first one, you have x minus y in a power. Okay? So the best way to approach this is if we can separate this power. So we can take this approach by write down the double integral, and then we can write this is e to the x, and then multiply with e to the negative 1. Right? That's our first approach. So we could have this to be solved. And what we can do next is we could take this y and x into groupings. Okay, so we can group all these variables. First, we can group that dy. Then we can group dy as y e negative y dy, and then integral of 1 to 2 for e to the x dx. Okay, let me write the dx in the front because we already get the answer directly for this one. Okay, and then we need to multiply with the integral of y e with negative y dy. So how to solve this y and e with power of y? At least we need to have, I think substitution will not really work, or it in some parts maybe works in the later part, but I believe if you try directly to integration by parts, you will get the answer directly. So you could use the integration by parts. So y10 plus, and then integrations, and then we have the answer is y negative y e negative y negative e negative y, and this is the answer. So this will be results in e to the x 1 2, and then negative 1 negative negative y negative 1 e to negative y, and then we plug in 0 to 1. Sorry, should be 0 here. Sorry, wrong number. Okay, so this will be start with e minus 1, and then this part will be negative 2e negative 1 minus e with power 0, or we could say that this will be 1 minus 2e negative 1. Or if you want to calculate in more clear equations, we could have, okay, you can just get stop here, but if you stop until this one, that's all perfectly fine. Okay, the second question. Okay, because we have x, y inside of these two fractions, then probably we just take the iterated integral. Okay, so we compute the first one with respect to dy. Okay, so 1 over y integrate become ln. So we start by writing the outer integral and then writing the inside one. The result will be x ln y. Okay, first that, and then the second is plus y squared over 2x. From, this should be from 1 to 2. Okay, we could evaluate first. So x ln 2, because ln 1 is 0, so x ln 2 plus 4 minus 1 is 3, so plus 3 over 2x, and then integrate with respect to the x. So now we integrate x squared over 2 ln 2 plus 2 over 2x, we will have 3 over 2 and then ln x, and start to evaluate from 1 to 4. So 4 minus 1 is 3 over 2. 4 to 16 divided by 2 is 8 ln 2, right, plus 3 over 2 and 4, write this here, and minus ln 2 over 2 and then plus 0. So we will have 15 over 2 ln 2 plus 30 over 2 ln 4. Or if you want to solve this, we can take this into 2 squared. So this will be having much more so 3 ln 2, 3 plus 15, this should be 21 over 2. Right? Okay. This is the answer. Okay, any question on this part? I believe it's not too difficult. Right? Okay, we can, I think, move on to the double integral on the general regions. So this part 1 here is about double integral over rectangle. So it should be perfect rectangle, which means that we are looking at the endpoint is perfectly a constant. Okay, that's symbolized. That is the perfect rectangle. Okay. Now the next one, we would like to see in more a general region, so we can have the endpoints is a function, not a constant. Okay, I think I will go to the next slide. Okay, now 15.2 will deal with double integral over general regions. So first we consider a general region as in this picture. Let's say we have this D, okay? We have this D. Now, suppose that the D is a bounded region, and which means bounded, that it means that it can be enclosed in a rectangular region. So we would like to make a rectangle outside of this D. Okay? Suppose that we have this. And now if we want to integrate function of xy, if you want to integrate this, then define a new function. We define a new function. That is the capital F xy. That in terms of maybe I will put the picture first to make it more clear. Okay, let's say we have this region. So the region here, the R, we have a rectangular outside of the D. The idea is, our objective, our goal is we want to evaluate D. So we are going to define a new function, that is this capital F, that has two definitions, okay, and a piecewise defined function. So first, the F is just as same as our original function that we would like to evaluate. Okay, so if xy is in the domain, okay, the D, and the capital F will be equal to 0 if the point is outside D or in R, but not in D. Okay, so we would like to use these definitions. Okay, and if this F integrable over the rectangle R, then we define that the double integral for fxy dA is equal to now this is our first approach. Okay, this is our first approach to define or to calculate, to compute a double integral in a more general regions. Okay, still we need to imagine there is a rectangle that is restricted the D. So what it means is, actually what we are going to look at is, let me give you another picture, maybe here. This is what we really have. So if you look on, if we take the graph of this capital F, outside of D, this will turn out to be 0, right? Because they are not mapping in any surface. The surface that can be mapped is just on this D, which is actually, these two are pretty similar, but they are different functions, right? They are different functions. Okay, now we are going to define our region D. So the plane region D can be defined at least two times. Okay, that is our topics for this 15.2. So there are at least two types. Okay. The first one is we have this. We could have maybe focus just the first one here. The second and third one is just the derivative from the first one. So if we have D, okay, and we have two different restriction line or curve, and it can be defined as a function of x. Okay, it's symbolized by G1 and G2. And let's say our D, okay, our D is the point. So x is a constant, but y will have a function of x. Okay, that means if D is it can be defined as this one. Then the integrations, this can be described as a b integration g1 of x, g2 of x, xy, dy, dx. Now we can write with this equation. We say that this is called the type 1. Type 1 of D. But type 1 or type 2, it doesn't matter. It doesn't matter. As long as you know how to deal with the functions. Type 1 means that if you can define those functions as a function of x, then we are going to have this kind of formulation. But also remember that sometimes some curves can be written as a function of x or function of y, right? So it depends on the situation, and it depends on which functions that are easier to be calculated. Okay. Because some functions in some forms, maybe they don't have the integral result unless you change into the other types. Okay. Okay, let me wait for a moment. You can at least try to look at and maybe take some notes. Okay. Here is more clear. Okay, if you don't have anything to discuss within this page, we'll turn to the next page. And if you feel it's too fast, please let me know. Okay, I will take times to let you, maybe if you want to write, or maybe to observe what is the formula and how to use it. I can wait for a while. Okay, let me go through next page. Okay, the other types, so we just have only two types. Okay, this one. So this is the, let me make it more bigger. So the other part is, of course, the function of y. So we have d is the constant for y, and then the x will be a function of y. So we will have h1 of y less x less h2 y. Okay. Then the integrations, the double integral will be, let me write completely. So always start the constant at the outside integral, and the inside will be the functions. F x y, this is the x dy. Okay. So the key important here is no matter what type the double integrals you might have, the important thing is how to write the equations. Okay. For example, if you have a function of y, then this part, the double integral, the outside part, this will be a constant of y. And the inside, this will be a function of x. Or function of y now, not function of x. It's x, so function of y. If your double integrals, you have constant x like this, right at the outside integral, and the function of x will be written here inside the integrations. Okay. Oh, sorry, should be y. Okay. Okay. Now probably let me give you some illustration on examples. So let's evaluate this x plus 2y and then dA, where D is region bounded by parabolas y equal 2x squared and y equal 1 plus x squared. Okay. Okay. Now the procedure, we have this region, right? How to evaluate this double integral? Now, this part here, this is the function, right? But it's not really necessary to draw this part, because we see that from what we have discussed, the important part is if we draw the D, or the area, the region. Now, what we need to draw is, so first, a quick recap that first sketch or draw the region, and then B, define a formulation, and then you can compute. Okay, so first we could draw our parabolas. So first we could start with the 1 plus x squared. Let's say that is our 1 plus x squared. And then y equal 2x squared, probably here. Let's say that's our maybe a little bit wider. Okay, maybe that's the point. Okay, so this is our D. Okay, now if we take, oh, maybe right here, 2x squared. Okay, now first we need to find the section, and I think if we check through some calculations, you say that this is 1 and minus 1, right? From here, plus minus 1. So this is 1, 2, this is also negative 1 and 2. Okay. So if we have this, and we already see that that this two function is already function of x, then we could already define that if we would like to calculate from negative 1 to 1, and then from the 2x squared to 1 plus x squared, this will be defined as double integral. This is dy and then dx. Now we could start slowly, and it takes time to integrate the inside. Okay. Integrate with respect to y. So x become xy, and y becomes y squared over 2, so y squared. And then you need to plug in these two equations. So if it takes slow, takes time for a while. So x to x squared plus 2x squared and then squared. Okay, and then minus, oh sorry, should be 1 plus x squared. Okay, now x 2x squared minus 2x squared squared. And still the x at the end. Should check all. This is 1 plus 2x squared plus 4 minus, this is 2x cubed minus 4x4. So we have minus plus minus, oh it's sorry, it should be plus, so it should be minus 4 minus plus 1 minus 3x4 minus x cubed, and then plus 2x squared, and then plus x plus 1, and then dx. Okay, we can integrate. Okay, and then input, and you may use calculator for some computations. So we'll get this is 32 over 15. Okay, because the important part for this one is not the calculation, but how do we define the functions? Okay, how do we define this integral setup? Okay. Okay. Okay, any questions? I believe still can follow, right? Okay, I hope you can still follow with it. I think most of you already asked the midterm result. Some still asking now, but wait for class ended. I will send you the results, okay? So if you haven't get the result, let me know. I can let you know your midterm result. Okay, we're going to the next example. Okay, so this is the first example. I believe the three steps here, essentials, is I think similar also with the calculus one when you deal with the area between curves in the integral chapter 6, right? So first sketch region to imagine how it looks like, and then define the formula from there. I mean, you need to pick out which functions you are going to use, function of x or function of y. After you put in the setup, then you can compute the integral. Okay, let me go through the next page. So another example is we have xy dA, double integral. D is region bounded by y equal x minus 1 and y squared equal to x plus 6. Okay, now first we could draw this. Okay, we could draw. And it depends on which preference you are going to use. And I think for both cases, it's still doable, but I think if you are using function of y, that's probably better choices, right? Okay, if we take the drawing and try to draw from scratch, okay, if you are not really good at drawing, or sometimes you are not getting any idea on how the graphs looks like, I hope you can review some parts on calculus 1 or maybe some math from your previous semester in maybe high school. Some functions like quadratic, the polynomial functions, the reciprocal 1 over x, the logarithmic, the trigonometry, they are, I think, essentials, okay, so that you need to right away know how to draw. Okay. Now first, if we look on this function, if we would like to take this as function of y like this, we could draw and we could find how this polynomials or this quadratic can have at least the roots from this functions, right? Okay. But then let's say we are going to have this y squared. So let me just draw quickly. Okay, let's say this is our drawing on this function. Now we could say that the part above is, we could say that this is 2x plus 6, and the part below is the negative part, right? if you want to take into this separate parts, but we could say that this is x equal y squared minus 3 over 2. Okay. Okay, now the line x minus 1, that should be going here, probably here. It should be, to make it easier, let me just make some, or maybe just take a little bit there. Okay, maybe here. Supposed to be connecting to the curve. So this will be our y, x minus 1. So this is 1, this is 1. Okay. Negative 1. Okay, we could check the intersections. So y plus 1. So y plus 1 is half y squared minus 3. We could write this is y squared minus 3 equal to 2y plus 2. So y squared minus 2y minus 5, okay, equal to 0. Oh, wait. Y squared minus 2y, oh, should be, let me, oh, should be not 3, should be 6. Should be 8. I think that's correct. Okay, now we have, I think that's correct, right? Okay, now we have y equal 4 and y equal negative 2. Now we say that the negative 2 is probably here, and 4 is probably here. So when y is 4, then this will be 5, 4. And when y is negative 2, this will be negative 1 and negative 2. Okay, that's the intersection. So we already get all the necessary required numbers. So we could say that the integrations of double integrals of x, y, dA, this will be equal. We could take the function of y, okay, for our case. So we could say that we are going to evaluate from negative 2 to 4. Okay, that is negative 2, 4, and then the integrations will take from the y squared negative 3 over 2 up until the line y plus 1, and then xy dx and then dy. Okay, we start with the inside integral. Okay, we say that this is x squared over 2 y, and then we have y squared, or half minus 3 should be okay. Make it easy to write this, and then write and input the y plus 1 squared over 2 y, okay, and then minus, or maybe let me write y and then y y plus 1 squared over 2 and then minus half y squared minus 3 squared. Okay. Okay, and then I think we can factorize 2 also. Right. Forgot to factorize. This is probably I will write the outside here to help. Okay, now we can this become this, and this becomes and then multiply with y, or maybe we can solve this first, then minus, so y squared plus 3, so 4y squared is 4 plus 4y squared minus 8. Okay, now we can have half integrations and multiply with y, so half y5 plus 4y cubed minus 8y and then dy. And then we can solve the integrations. Well, we could compute the integrations, I believe. Don't really need to write all this. But let me just write this. This will be minus 6. So 12. Oh wait, should be 4. Sorry. So this should be 20. Okay, now I think we can take this into, oh, wait. Forgot to write this one. Plus 2y minus 8. So we can say plus 2y plus 2y squared. And then this one becomes okay. Now we could take this, compute, and this should be equal to 36. Now if you let if you use these two equations, okay, so if we are using the later part, so we would like to define another function of x. If you would like to, that this will be for g1, we will have 2x plus 6 and x minus 1, and this will be having two different, so this is if x is from -3 to -1, and this will be x minus 1 if from -1 to x 5. So which means that this is precisely this part, okay, the bottom part. Let me draw with maybe just make sure this part, okay, and here, okay, this is -3 here if you check the point, the vertex. And similarly for G2, So you could say that if you would like to calculate using function of x, it is possible, but you will see that it is going to be really, really complex and ugly in equations. Okay, that's what we can do for if you want to force the function of x. So I believe this is not an easy task. Compared with this one, it's more durable, more human, right? This is I think yeah, really difficult if you want to use it in your calculation. Okay, any questions over here? I will give you one last section today. That is the how to change the integration order. Okay, that is pretty useful. You will use this, I think, not only for this calculus, but I think for more advanced courses in the future. This will be, I believe, really helpful to observe some integrals, some double integrals, or multiple integrals if you have. Okay, let me move to next section. So if you'd like, you can take screenshot here. Okay. Okay. Let's say we have double integrals of 0, 1, x, 1, and then sine y squared dy dx. Okay, if we would like to evaluate this, so imagine that we are using this first iterated integral with respect to dy. We integrate sine y squared. Can we integrate sine y squared dy? Will be difficult, right? If you want to take substitution, for example, y squared is u, and then we have 2y dy, and then this become du, then you will still have this y that is appear, and there's no cancellations that available, right? Then this will be impossible to do, and this is not elementary, so which means that this integration is slightly impossible. So what we can do is, if we are going to solve this, one way to do it is to change this in this order, changing the order of the integration. That's one way. And how to do that? The first thing is we are going just to focus on this order, the double integral. Okay. Now, if we define and look at this at the double integral, we see that the x is from 0 to 1. So we have x is from 0 to 1, and y is from x, right? Y is from x to 1. So in the y-axis, it has some restrictions that it says that it will be equal x at this endpoint here, which means that it has a line equation. It has some line equations. Okay, so if we draw in a more imaginable for this d, we could say that from 0 to 1, that is our x, right? And let's say we have the line of y equal x. Okay. Now we have at least two possibilities that we can look at from this area, which means that it can be this area or this area. Which one, right? So if we look carefully, from 0 to 1, that is our x, and y is from this one up until the y equal 1, which is this. So this will be our area, okay? I hope this is clear, okay? So so let me write the original one. This is the original one. So if you would like to change this integrations, becomes dx and dy. So we are going to start and write dy in terms of its constant. Okay, the constant of y start from 0 to 1, right? So we are going to write this is 0, this is 1. And how about the x? The x will be, it start from 0. Okay, start from 0 and into y. So we could see and imagine, oh sorry, the line start from this x equals 0, and then move here, and we could say that it's perfectly aligned and it follows this y equal x or x equal y. So this will be, we can say it's x equal y, okay, up until here. Okay. So there are a lot of questions like this to change the integrals. The idea is you need to keep in mind, okay, every time you need to change your order of integrations, you need to be more imaginative. Okay, you can imagine in a 2-dimension visual. Okay, now if we change to this integral, now we can solve this. For example, if you would like to solve this integration, we just take this sign and then we can put 0y dy, and then if we are going to check this, and this will be y sine y squared dy, and this is perfectly can be solved by substitutions method, right? You can substitute u y squared, and then du will be 2y dy, and then we can have half in the front. Okay, sine u become cosine u, so it should be cosine y squared from 0 to 1, and we could say that this will be equal to half of cosine 1, or we could write this should be negative, sorry, should be negative. So we could write this is half, so we could exchange this into 1 minus cosine 1, and we can solve this. Okay, so change the integral orders can be really helpful for some double integral case. Okay. And property of double integral is similar to what we have in the rectangle, the double integral in rectangle. So if you have a constant, you can factorize the constant. If you want to add the integral, you can add the integral. You can separate the integral. If they have two functions inside, you can separate. And then you can also, you can make it, for example, if you have this region here, D, you can make it 2, D1, D2, no problem at all. Okay, before we end, the next property that we have is if we have just dA, double integral dA, this will be equal to the area of D. We will explain this later on Thursday. Okay. So I think that's all for today's class. Okay. So don't forget to check the Moodle later this, hopefully this weekend. I will put the link for the quiz, the online test on the Moodle. Okay, QR code. Okay, let me give you the QR code. QR code. So if you haven't scanned, please scan the QR code so that I know that you are attending the classes. Anything you want to ask, discuss? Okay. So suppose that online lectures until the 22nd of May. Still, I think we need to wait and see what is really happening in the future. So whether the online class will be continue or just up until the final exam. But if we have a physical class in probably in the end of May, I would like that the physical class also include one more quiz. Okay, one more quiz, and then the final exam probably around the second week of June. Okay, second week of June. Probably that is my schedule, my plan. And in between the weeks, I hope I can get first is some feedbacks, and the second is maybe another additional videos that can be uploaded for you. Okay. Yeah, the online quiz will be just like online test like you did before in chapter 11. Okay. So I will just give you the link, and you could click the link, and the question will be a random questions that will be having different time limit. Okay, so you need to prepare at least 2 hours. The average score, wait a minute, for the class is, let me check, is 72, the average score. 72. Okay, so if you haven't get your midterm score, you can email me. Okay, you can email me. I will let you know your result. Okay, if there is no questions, okay, if there is no questions, I will end the lecture, and you may leave the online meeting.